Everybody is developing cloud-native applications. How do databases run in the cloud? On the SQL team, we have been developing a hybrid multi-cloud platform to run and bring the learning that we have from running SQL managed instance in Azure public cloud to you as the developers in DBA community to empower you to run your favorite database engine SQL and other Azure data services outside of Azure. Hi everyone, I'm Dhananjay Mahajan. I'm a Principal PM Manager on the Azure Data Platform team working specifically on Azure Arc enabled data services. And I'm here to talk to you about how we enabled Azure Arc enabled SQL managed instance to run on a hybrid cloud using Kubernetes. Many of you know me as DJ Data from Data Exposed. So let's get started and understand more about this. At the end of the session, you'll have a good understanding of how Azure Arc enabled data services run in Kubernetes, along with practical guidance on how to create an infrastructure configuration to run your data services, SQL managed instance, Postgres, and other data services in the future. This applies to whether you are running your own Kubernetes on premises or using one of the managed service Kubernetes on a variety of hyperscaler platforms like Azure Kubernetes Service. Now, first we'll start by understanding what the journey of a few of our customers who have been working with on Azure Arc is like. What is Azure Arc? We'll explore the cloud native application concepts, the data platform that is needed to run these, and then we'll go under the hood and understand how we took our SQL managed instance engine and put that on Kubernetes and understand how Kubernetes, the benefits of Kubernetes are being used. Once we have gone through this, it's important to have certain operational considerations in mind when you start using Azure Arc enabled data services to run SQL MI on your own Kubernetes. And we'll talk about next steps in learning. Now this presentation dives into the implementation detail, so I'm recommending that you first review other presentations which showcase the various features in Azure Arc enabled data services. In this session, we'll go into the internal design of the product so you can derive the best value and learn just enough Kubernetes to be sounding intelligent, smart, and operate the product in an efficient way. Now let's look at what the journey to the cloud looks like for hybrid applications and data platforms for developers and database administrators. As developers and administrators have adapted to the innovation that cloud platforms and hyperscalers are enabling, they're dealing with some new challenges. Cloud innovation has radically changed the way applications are designed, built, and run. For an application to be truly portable and to be built in such a way that it needs to write code once and run everywhere, it is more than just shipping and packaging the code. You need the cloud services, you need the container infrastructure, you need the orchestrator, as well as DevOps practices. So not only do you need to change the code and the technology, but the way you use the tooling to deploy, secure, and operate it. So it's a whole new paradigm shift for many of our customers, our users, our developers. And it's clear from the conversations that I'm having with those of you in the community, as well as our customers, that the app of the future is cloud native. Cloud native is the way to go, which means it's designed to take full advantage of the latest innovation you're getting in hybrid cloud with containerization, microservices, and DevOps practices. They're intelligent, and these applications are infused with AI to use the data and provide you actionable advanced insights. And we're taking advantage of open source technology and libraries from across the community to give you the best. Kubernetes has become such an integral part of the cloud native world that with Azure Arc, our goal is to ensure that we don't get in the way of your bet on that Kubernetes platform. As developers are designing new applications, DBAs have to create a service offering that is consistent in the cloud in terms of offering data or application services or serverless. Using cloud billing, they can create some cost controls. Cloud enables operating services at large scale through automation. You always have to be able to use a versionless version of whatever service you're running. It has to be always up, and data services have to be on premises. Data is a prime asset for large and small businesses. As you use the flexibility of the cloud, you want to make sure it's secure and governed. So now let's talk about the key scenarios where we see customers using this. I have a customer who is a financial banking customer, and they want to offer database as a service to all their internal line of business application owners, whether they're talking about investment banking or they're talking about retail banking. A consistent experience where they can provide cloud billing. Then I have another set of customers who are in the retail business. What they want to do is utilize the automation to be able to deploy these databases in a highly available environment along with their applications and keep all of their data services up to date, versionless, without impacting the downtime, and provide that consistent portable data experience in any cloud so that they can design and develop the application once and deploy it anywhere. To use it in their retail industry, in retail stores, so that they can get the best insights as to how they manage their inventory, how they manage their personnel, how they manage their orders, and be most efficient. Especially in government as well as banking sectors, security and governance has become important. In certain regions, I have customers who are actually using Azure Cloud and public cloud, but due to restrictions or rules and regulations brought in by the government, they want to bring some of that data within their sovereign regions. And they want to use it with security and governance. And then we want a consistent way where I have a manufacturing customer who uses data coming from various sensors using IoT, and they want to analyze that data to understand if their factory floor is running efficiently. They want to do this quickly across hundreds of factory deployments that they have, being a global, but they can't afford to have the same connectivity to the Azure cloud from all their factory locations to get those data insights. So they want to provide those real-time insights with low latency and throughput. That's where many of our customers have adopted Azure Arc Data Services, which is a hybrid multi-cloud platform that we are building to use your data in all the above and more scenarios coming in the future efficiently. Let's explore the architecture of the cloud and truly understand how we can use Kubernetes to run stateful services like databases. Azure Arc is the technology which I was mentioning my manufacturing customer is using to write an application once and run it on the manufacturing shop floor and deploy it to hundreds of factory locations. Azure Arc helps them unlock this hybrid scenario by extending Azure services that they're using in the public cloud to any infrastructure outside of Azure. They can now manage and operate existing and new resources like servers, databases, applications consistently at scale whenever it's hosted inside Azure or outside Azure. Azure Arc enabled infrastructure and our Azure Arc enabled services are two different approaches that we have enabled through the Arc platform. Infrastructure lets our customers collect resources, inventory them, which could be living outside of Azure or in Azure public, and operate them in a native way as Azure resources would be, equivalent to the infrastructure as a service model that you have in Azure. Data service gives customers the flexibility to deploy fully managed Azure services relating to data anywhere outside of Azure public. It could be outside on premises as well as third-party clouds like Google Cloud or AWS. Equivalent to the platform as a service model that you have in Azure, this provides the application developer a truly cloud-native experience to consume databases and other data engines coming in the future. So what essentially are the real ways how you can harness data insights? Let's take one of our retail customers who is a grocery chain. With Azure Arc, they can innovate innovation via the cloud data and AI capabilities to build next generation applications and gain fast continuous insights. They can improve the operational efficiency and reduce IT overhead through cloud automation and consistent management. And they reduce the exposure through an integrated multi-layer security and data governance practice. And that's where Azure Arc enabled data services comes in. With Azure Arc enabled data services, we bring the best of Azure with its cloud data management capabilities to any infrastructure, no matter where the infrastructure lives. This can be on your existing on-premises environment, in other third-party public clouds, or even at the edge, like we have seen in our retail and manufacturing customers. These services can run anywhere and bring much needed streamlined experience across your data workloads, so your applications can get access to the data where they need to. Here's how it does it from a functionality standpoint. Azure Arc enabled data services will deliver that always up-to-date experience. End of support is happening for SQL, some of the SQL customers. That's a thing of the past. You can benefit from an evergreen version of your service because it's always patched, always up to date with the newest features to maximize efficiency and minimize your disruption. This can be done with very or zero downtime. Get industry-leading multi-layered protection with built-in security that we have developed in Azure. With a comprehensive encryption, including transparent database encryption and always encrypted databases, and policy and control, so you can control who gets access to the database. Optimize your performance by scale up and scale down using some of the elasticity that you get from the cloud. And with Azure Arc, your teams can leverage the tools that they are familiar with, so they don't have to retrain themselves. The consistency means a vastly simplified DevOps experience by reducing overhead. Deploy a 3 replica SQL managed instance with full HA capability in 2 minutes with a single click compared to hours. Gain that unified view into your query performance, storage capacity, error logs using dashboards directly from built-in monitoring. That's the power of hybrid multi-cloud. Now, enough of this talk of selling what the product is. Let's dive into the technical details of how things have evolved from cloud native concepts to come in, a cloud native practice to come in, and how we are evolving to the next generation database and data services that you want to use. Now that we have explored that quick journey into the cloud and its roadblocks, let's look at how modern apps are being developed and the new concepts. Kubernetes here is rapidly becoming a standard platform for orchestrating containerized apps, with more than 50% enterprises running mission critical containerized cloud native applications on thousands or more hosts at scale. Now you want to deliver a consistent database experience with your choice of clouds, Azure or other clouds. Many of the data applications on the edge require low latency. To get real-time insights like manufacturing, these can be delivered if data services run closer to where data is aggregated. Now, applications have started transforming from being those monolith applications that run into VMs to the ones running on the cloud using modern architecture, which are cloud native. These applications are built using microservices, containerized, and using serverless APIs. So once you build this application, it can run in any cloud if you use some general concepts that we should see. So let's take a step back and try to understand what are these new concepts coming due to cloud. One key concept is containers. What is a container? Slice of an OS to run multiple applications in a single OS is what a container is. When traditional virtual machines technology was created, that was hardware virtualization. Hyper-V was one of the technologies that came out of Microsoft, and we created Windows Server containers just like Linux containers as part of it. Containers are operating system virtualization. Typically, you can run one application per service per container, or you can have a more complex application with multiple containers. Containers and apps share the life cycle. Each container has an isolated view of the operating system, which makes it easier for it to be updated, patched, deployed at scale, deployed across clouds. All of these concepts make it easier for you to develop those modern applications. Now, why are we worrying about Kubernetes? Many customers, the Kubernetes community thinks like, oh, Kubernetes is great for running, applications that don't have state, or what we call as stateless applications. Databases, bad things to run on Kubernetes. That's actually not very true, and I'm going to, destroy that myth in today's talk. But what is Kubernetes for those who are new to it? I want to show you just enough about Kubernetes concepts so that you understand when you start using Arc-enabled data services and when you start having discussions with your infrastructure folks. Kubernetes is an open source system for orchestrating and automating deployment, scaling, management of containerized applications. What Kubernetes does is it abstracts away complex container management and provides you with a declarative configuration to orchestrate containers in different compute environments. Kubernetes deployment is called a cluster. A Kubernetes cluster consists of one or more nodes on which it runs. So they may have multiple worker nodes, but one or more master nodes. Both the control planes, which is on the master node, and the node instances can be physical devices, virtual machines, or even instances in the cloud. The master node is the control plane that manages the application. Think of this as the hearts and brains of Kubernetes or the cluster that you are running in. And it manages the application containers that are scheduled to work on the worker nodes over here. As you know, the master node or the head node, the control, or also called as the control plane, manages these worker nodes and the pods that are running inside of that worker node. In production environments, the control plane usually runs on multiple computers so that it's highly available, clustered for fault tolerance, and made sure, because if the control plane goes down, the whole cluster is down. The control plane receives input from the CLI, and it takes requests to spin up new applications, new nodes. It is not recommended that you run workloads on the master node. So now what happens on the worker node? A virtual or physical machine that contains services necessary to run containerized applications is called worker nodes. The worker nodes host pods that are components of the application and orchestrate to run those pods on this node. You can scale up and down just by increasing and removing nodes dynamically, which is the beauty of Kubernetes. Arc runs SQL managed instance on these nodes as worker node pods, as well as the data controller. Now let us walk through the major components of the Kubernetes architecture, the major Kubernetes objects, so that we can understand how that works for databases and SQL managed instances, and how we get the best out of Kubernetes capabilities. We'll go through the major components such as the master node, the worker node, and how workloads are configured. And then we'll look at the underlying network storage components and security. just enough detail that you should know so that there is no harm when you start using Kubernetes for running your databases. Now the control plane has components that make global decisions as well as detecting and responding to cluster events. Cluster events such as failures of pods or nodes. Kubernetes relies on administrative services running in this control plane. These services manage aspects such as cluster component communication, workload scheduling, cluster state persistence. Arc Data Services heavily uses all of these for running the database instances with high availability and with persistence. While you will not deal with these components, it's good to know what those are. One is the API server. The API servers exposes the Kubernetes API, and you'll work through kubectl, which is a command line interface to talk to its RESTful endpoint, which is its front end. It tracks all the components that are running in the cluster and manages the interaction between them. It consumes YAML and JSON, and sometimes you'll have to work through it. Then comes the scheduler. And the scheduler ends up scheduling pods on these worker nodes over here. If there are no suitable nodes, the pods are put into pending state. That's where you can see if you run out of resources and the scheduler can't find a pod to run your SQL managed instance or the data controller, it might get suspended. It watches the API server, creates those pods, and checks on what new tasks are coming on. And that's how it keeps the service running. A couple of other things is the kube controller manager. The controller manager watches for desired state of the objects, and it manages and watches the current state through the API server. It takes corrective steps and actions to make sure the current state is same as the desired state. It is the controller of controllers. And we've used this controller pattern by creating a data controller so that we can state what is the desired state of the SQL managed instance that we are running in the Kubernetes cluster. It runs controller processes. Logically, each control is a separate process, but to reduce the complexity, they are all compiled into a single binary and in a single process. Now let's go through the worker node. The node components that run on every node, maintaining running pods and providing the Kubernetes runtime environment. Pods are components of an application that run in the containers, and we'll go through a little bit of detail later on this. As the worker node or compute node, each node contains the necessary service to run these pods, and they're managed by the control plane. Kubernetes cluster needs at least one worker node, but normally you can have many to give you high availability. Pods are scheduled and orchestrated to run on nodes. You can scale up and down these pods. And as I mentioned, pods is the basic unit of work or the smallest deployable unit of computing in Kubernetes. Pod is a group of one or more containers. So like we'll create a pod for data controller, we'll create a pod for SQL managed instance. It's a thin wrapper around one or more of those containers. This is how our Arc Data Services resources are run on several nodes. Then there are a couple of things called kubelet and kubeproxy. The kubelet is an agent that runs on each node, and it's a conduit to the API server, make sure that containers are running in the pod and are healthy. And it instantiates and executes the pods within those nodes and watches the API server if the API server sends it new tasks. The kubeproxy is a networking component. It manages and plays a vital function of managing all the networking connections between the pods. It manages the IP translation and routing. It becomes a networking proxy that runs into each node. And it also maintains the networking rules and policies. And finally, container runtime. You'll never have to deal with it. Hopefully that's something the infrastructure admin will decide. But if you, for some reason, your application is built for a specific runtime, like a Docker runtime or CRIO is another runtime, you may need to make sure that that's compatible. Then we go into the workload itself. The database and applications are workloads, as I mentioned. They use Kubernetes for its portability, for its extensibility, for its self-healing, so that auto placement, auto restart, auto replication, auto scaling can all be done. In addition to the pod, there are a few other concepts you should know. One is a deployment that provides a declarative update for the pods and replica sets that describes the desired state of the app. So deployment creates a management object one level higher than the replica set and enables you to deploy and manage updates for pods in a cluster. Deployment handles replica sets. It automatically creates with the deployment. Deployment is the most common way for you to deploy apps in Kubernetes. Now I talked about replica sets. Replica sets is to maintain a stable set of replicas. Let's say you want multiple replicas of a SQL managed instance running. So if one fails, the other one is up and running. Well, replica sets is used to define the number of pods you want running, which means the number of SQL managed instances in our case. Kubernetes supports self-healing applications through this concept of replica sets. And replication controllers. The replication controller helps in ensuring that a pod is recreated automatically when the application is down or crashes or the pod crashes. It helps in ensuring enough replicas of the pod application are running at all times. And then we have something called stateful sets. Now, databases are stateful applications. So stateful sets is used to manage stateful applications and persistent storage. Storage stays associated with a replacement pod so that when a pod goes down and a new comes up, the volumes persist when the pods are deleted. That's how you don't lose your data, right? Even if the pods are gone. We'll talk a little bit more about storage and persistent volumes later on. Stateful sets run stateful pods with a stable identity and provides guarantees about the ordering and uniqueness of these pods. And finally, namespace. Namespace is nothing but a collection or a grouping of resources with a single within a single cluster. And it's used to give you a scope for role-based access control and all kinds of scoping in terms of policy. The names of resources need to be unique within a namespace. You'll see later how Arc SQL Managed Instance uses these workload components to spin up an entirely new service and database to give you platform as a service. Now a few more concepts before we dive into the underlying layers of the infrastructure. One is configuration primitives called config maps. Now config as code is a big paradigm in cloud. So you define something that you want in configuration and that gets done declaratively. Config maps is a way of storing non-confidential data in key value pairs. So the pods consume these config maps and get their environment variables, command line arguments, and so on. That's a way that you can decouple the settings that are environment specific configuration from your container images and makes your application very portable. Secrets are basically secure keys, passwords, tokens that you want to store along with your application. Now let's dive into the networking layer. Now, networking is an important part of Kubernetes platform that abstracts the components internally through the network overlay, exposing these services externally for applications and users to consume. It's usually not something you'll have to worry about until it breaks, and then you'll have to diagnose and debug why the load balancer is not working, why the service is not responding. So let's understand the concepts. Service is used to expose an application deployed on a set of pods using a single endpoint. It maps a fixed IP address to a logical group of pods. Service provides a stable networking for pods by bringing stable IP addresses and DNS names, and provides a way to Kubernetes to configure a proxy and forward all this traffic to the right pod. So the communication between nodes, pods, users of apps, internal, external, north, south, or east, west is all taken care by this concept of ingress, which exposes HTTP and HTTPS routes from outside the cluster to services. Traffic routing is controlled by these rules, and this is how ingress controller works. Like I said, applications can talk to SQL MI or Postgres as a service through the service name, and tools can communicate it with the data controller, and deployed load balancers have to work with these scenarios. And that's how Kubernetes has abstracted it all away. Storage is yet another important set of objects that you have to deal with. That's because databases require storage. In fact, they work and you consume a lot of storage, and you want to do it efficiently with optimal performance so you can meet the required application performance and availability goals. Kubernetes has a number of storage types, and the important objects running there are persistent volumes, which are a low-level representation of the storage, persistent volume claims, which is a binding for a pod and a persistent volume, and a storage class which allows you to dynamically provision these persistent volume depending on whatever storage is available underneath it. Persistent volume is a low-level representation of the storage. It's an abstraction from the physical storage device that is attached to the cluster. PVs can be mounted into a pod through persistent volume claims. PV is a resource to the cluster that can be provisioned dynamically using storage classes, or they can be explicitly created by the cluster administrator. This is how data services runs databases on Kubernetes. Now, persistent volume claims is a binding between the pod and the persistent volume. Pod requests a persistent volume through a PVC. PVC is the request to provision the persistent storage with a specific configuration. And then PVCs describe how much capacity is needed and characteristics of the pod, and cluster attempts to match these at the best and provide that and provision it. And storage classes allow that dynamic provisioning for persistent volume and PV persistent volume claims. Storage classes are used in conjunction with PVC that allows the pods to be dynamic. As an experienced developer and DBAs, you know very well that configuring the right storage is important to give you that great performance. It is not, if not done well, it can make your apps and services very unhappy. So something to really think through and keep in mind. Now let's come through the last set of Kubernetes objects we have to deal with. That's been a lot we have covered so far. Applications and data have to be secured. Kubernetes object that helps services with authentication and authorization use Kubernetes role-based access control. Service accounts are used to authenticate and authorize requests by pods to the Kubernetes API server. Service account provides an identity for processes that run in a pod. Role defines what can be done to Kubernetes resources. Role contains one or more rules that can represent the set of permissions. After creating a role, you assign it to a user or a group of users by creating a role binding. Cluster role is the same thing as a role, but across the entire cluster. And role binding is used for granting permissions to subjects. Role binding holds a list of users. Subjects can be users, groups, service accounts, and a reference to a role. So this role binding brings that on a namespace based scope. So here you see how you can use role binding to reference to a role for each namespace separately and control authorization to certain areas. Cluster role binding is that same concept at a cluster level. A securely designed multi-cloud service is an important and detailed discussion topic. It is outside the scope of this talk. We have already covered a lot. Now, let's take a pause, internalize all those Kubernetes concepts we just learned. We reviewed the challenges on the journey to the cloud native data application development. We understood the concepts of cloud native platforms and applications. Now that we have core Kubernetes concepts, the objects and how they can be used, let's take an example of how Arc-enabled SQL managed instance uses Kubernetes to deliver a hybrid multi-cloud data service. An interesting design debate has been ongoing in the Kubernetes community since cloud platforms were not very known to be stateful applications and databases, but recent development enhancements have started in Kubernetes, which we just talked about, and we have started developing an Arc platform where we use those fundamental tenets to make sure it's used to efficiently run mission critical databases. Let's see how SQL Managed Instance works on it, but let's start first with the important design principles, because this is SQL Managed Instance today. We will also bring in Postgres and other databases and data services in the future. So let's look at the design principles. Let's look at how they're applied before we go into operational considerations. Please note that this is not an architecture implementation drill down of Arc-enabled data services, but to explain to you the subset of core services that will impact you as a developer and administrator. At the outset, when we started designing this hybrid cloud, multi-cloud platform, we wanted to make sure we deliver to you a consistent experience for application developer and administrator. They should have minimal effort to use SQL Managed Instance and be able to use it with your choice of tools which you've been using today with Azure or in the past or in future, and be cloud ready. We decided to provide that dual interface, so you can either use Azure Public Cloud APIs like the ARM APIs and ARM tools in the ARM portal, or native Kubernetes users can also use the native Kubernetes API and native toolset. This allows you as a developer or an administrator to use all the range of tools and vast number of open source tooling and support that's out there to empower you to design and use new applications. So what were some of the design principles that we used around resources? For resources that require a DevOps engineer, infrastructure admin, or developer to interact, we put that into Kubernetes. For a resource that's manipulated from Azure centrally and inventory or deployment, we created an Azure resource to reflect that resource that is in Kubernetes. For providing role-based access control outside of Azure to the resource, we use Kubernetes RBAC and Kubernetes concepts like namespaces. For objects created as part of that DevOps, GitOps pipeline, use native Kubernetes. For declarative actions, use Kubernetes objects. For imperative actions, use APIs. For anything that requires quota, limits, request, use Kubernetes objects. And if you're using labels, it's Kubernetes objects. If you're using tags, it's Azure resources. From an operational standpoint, we want all major standard Kubernetes resource APIs to get a better experience. We want to expose all imperative operations through AZ-CLI as well as a symmetric interface in Kubernetes. We want to offer sync and async mechanism for all the operations, especially those that are long running. And we want to use native Kubernetes logs, kubectl describe, kubectl get job, so that you can start using the management tooling and a whole list of open source tooling that's available to manage Kubernetes. So first, before we dive into the overall architecture, let me explain how a SQL managed instance workload is deployed in Kubernetes or Postgres. The way we architected Arc-enabled data service to meet the requirements is to provide a local Azure Arc data controller using that same controller pattern I mentioned about to operate all the needed management capabilities required by our data services, even with or without connectivity. So this service can run in a connected mode and can use a lot of the Azure services combined, but it can also run quite effectively in a disconnected or indirectly connected mode. First, you deploy your choice of any CNCF certified Kubernetes distribution or cloud service on the infrastructure of your choice. Next, you deploy the Azure Arc Data Service Controller as a set of pods on the Kubernetes cluster. These pods provide all the management capabilities right there from the Kubernetes cluster. Next, you're ready to deploy the actual SQL managed instance of Postgres using the Azure portal, Azure Data Studio, or Azure CLI, or even Kubernetes native tools like kubectl, Argo, Flex, and so on. In the directly connected mode, which means you're connected to Azure outside of your cluster, Azure Arc agents continuously send data to Azure, and you can operate, and this is data which is relating to the metadata of the SQL managed instance, not the database itself, but it will help you operate all your databases wherever they reside across all environments from a single point of control, which is Azure portal, the Azure ARM API, and the Azure CLI. In indirectly connected mode, all the data resides within the cluster and you can export it manually offline, but it provides you a mechanism to use Azure Data Studio or Azure CLI or the Kubernetes native tools. From there, if you are in connected mode, you can connect to database instance using standard application data access libraries or tools, just like you do today. So the application doesn't even have to know this database is Arc enabled. At the end of the day, this is your database, your data, your application, and you want the best flexibility when we design that architecture and provide you that during operations. And less, whether you have greater or lesser degree of connectivity. The more connectivity you get, the more advantage you have on using some of the Azure services. So now let's see how this is all put together. Now that we know the Kubernetes concepts, we know the design principles, let's look under the hood on how our favorite database, SQL Managed Instance, runs on top of this platform. This is also a foundation for running Postgres and other databases. So the architecture is somewhat similar. And this architecture diagram is very busy, but I'll try to make it easier for you. Here's the public cloud Azure. That's where everything in Azure resides. Maybe you have running Azure Data Services. And below this line is everything that's either on premises or a third-party cloud like Google Cloud or AWS Cloud. This is where your Kubernetes, this whole thing is your Kubernetes cluster, and this is where your master controller is running, and these are running on a master node or one or more, and these are worker nodes where individual SQL managed instances will get instantiated. In fact, all of the Azure Arc machinery runs on these worker nodes. And then some of the capabilities of Kubernetes abstract the underlying hardware on where all of this works. So you should really not care where this is running, other than offering that as a service on every cloud. The Azure Arc Data Controller and the SQL Managed Instances and Postgres are all running on worker nodes and launch and execute in more pods. The data controller runs in its own Arc namespace along with other pods, whereas individual SQL managed instances will be running in their own individual pods on separate namespaces within the cluster. All of this requires each individual namespace to be configured so the data controller can own all the resources in a namespace. The data controller itself has several pods, as you can see, and it plays the various roles, whether it's scheduling the data services, telemetry, the billing services, sending data back and forth to Azure, integrating with the Azure API, converting all the Azure ARM calls into Kubernetes calls so it can talk to Kubernetes. All of that is done by the data controller, and it interacts with Kubernetes through the Kubernetes API, which is running in the master controller. SQL managed instance requires state to be persisted in the available storage below it. The data controller exposes an API to deploy SQL managed instance using stateful sets. To store the data of the database instances, storage class is used in conjunction with persistent volume claims that allow pods to be dynamically requesting new storage. So whichever platform it runs on, it picks up the right storage on that platform. Now, when a pod fails, a new one is spun up by the scheduler, and immediately a persistent volume claim is used to attach the persistent volume to it. So you don't even know when some failure happens, you just are able to continue. The volume persists when the pods are deleted. Pods are deployed and updated individually and in order. Now, in the high availability disaster recovery scenario, replica sets are used to provision multiple secondaries to one primary database, each with its own associated persistent volume. If one of the SQL managed instance pod goes down, it spins up another one. And if it's a primary, a secondary one takes over as the primary, and the application has minimal disruption. Lastly, I want to also call into attention that latest updates, latest security patches are all delivered through the Microsoft Container Registry to the data controller and the SQL managed instance. That is reflected with our own custom registry. Most of the important Kubernetes objects are reflected in the Azure portal, allowing the user, whether it's a DBA admin or the developer, to interact with it, both using the Azure ARM API and the Kubernetes API. So kubectl and OSS tooling can be used to access through the Kubernetes API. That is how developers and DBA admins can continue to use the same tools, use the newer APIs and newer tools, and open source tools. That was a quick, brief architecture overview. A lot of detail in each of that pod. And for example, the metrics pod and the billing service itself can be wrapped open, and we can talk about this, but that's beyond for some other day. Let's take a breather. And next, now that you understand how things are implemented, you'll ask me, DJ Data, that's a lot of talk. Give me some practical advice. How should I get started? This is exciting. Let me get started on this quickly. Given the implementation, I'll give you some tips and tricks. So you look like super smart using your SQL managed instance in any cloud, whether Azure or outside Azure. A wrong decision here can result in problems that could be hard to fix post deployment. Azure Arc will be giving you the control over this infrastructure component, so it's important to understand how you can best use these services and infrastructure. You have to remember that if you're running SQL on premises, there are some additional considerations than running it in a third-party hyperscaler as a service, Kubernetes as a service. Now, you might remember we earlier on covered Kubernetes storage as exposed through a storage class. The persistent volume in the pod on Kubernetes cluster is used to manage the lifecycle of the volume. The container storage interface is the plug-in way to extend storage for Kubernetes. So different vendors come up with their own container storage implementation that will give you various features like volume snapshotting, cloning. So it's very important to select the right storage. For example, if you're taking backups, you need read-write RWX capabilities on the CSI provider. If it doesn't have it, it's going to fail. Now you can extend this storage easily by adding more to the current size and expanding on the volume. All CSIs do not provide the resizing capability. So again, be careful about which storage plugins you're selecting, and tell the infrastructure owners that are running Kubernetes to make sure you have the right CSI plugin deployed. By default, a pod is deleted. There is action the provisioner needs to take, whether to clean up or reuse the data. In production, do not set the delete policy. Reclaim will leave the persistent volume even after the pod is destroyed, so you don't lose any mission critical data. Persistent volumes can be manually cleaned up later on or using some kind of a cleanup script. Now, there are different types of persistent volumes, right? As I told you, there's data where most of the database files are stored. Then there's log where text input is stored. And then there are backup files. Not all pods are using all these three types. So data is the main part of persistent volumes. Logs will have text outputs, agent logs. And so use those or maps to var log. Then we store the database backups file in a backup. To improve performance, store data in the fastest storage, store backups in kind of slower storage so you're cost efficient. Each pod requires at least 2 persistent volumes. So estimate your persistent volumes based on the components. Data controller, metrics daemon set, and components will result as more and more storage usage. Metrics are stateless, so you don't have to persist. Special storage class, empty dir storage class can be used, and if used, it provisioned to the node itself. If the pod moves to a different node, then it's going to be lost. So use that carefully and wisely. What are some of the other tricks on premises? All of this is based on how Kubernetes is configured. To set up a high performance environment, if you build a Kubernetes cluster on bare metal, you may have to use Docker configuration. You want to relocate from root partition to a better performance on separate storage files. With NFS storage or Echelon or some of the high performance storage, SQL MI uses the 4.2 and above versions of CSI driver support for this. So you're getting a lot of storage capabilities available to you. For highly available configuration, make sure that you have efficient communication between the nodes and use those fast communication paths, and use the load balancing capabilities of high availability that provides from Kubernetes. Now, Azure Arc has 2 tiers. One is called general purpose, which uses a simple Kubernetes type recovery mechanism where pods come back and that connect to persistent volumes, which creates some time of disruption on the application. But in business critical tier, you have the high available disaster recovery deployment where you can create replicas and give the application high availability. Looking at storage, you can configure RAID 0 for local storage for advanced scenario. You can also use other scenarios, have sufficient persistent volumes pre-provisioned for better performance. For local storage, pods when deployed pinned to a node. If the node dies, Kubernetes cannot deploy the pod to another cluster and it gets pinned to that node. And summarizing the storage requirement, pick the storage class based on the performance characteristics you want. Set a default storage class for most workloads so you don't have to keep picking that up again, and it's all automated. For local storage, remember that pods are pinned to the node, so you don't want that happening. And cloud platform storage class gives you price performance as a key factor. Customize the storage class based on the persistent volume and the workload that you have in mind. Wow, that was a lot of packed information for you. Where can you go for more learning? Here's a whole plethora of sources that we have created to give you that additional learning. and introduction to Arc-enabled data services. We have a great hands-on experience through Jumpstarts, and I would highly encourage you to go to some of the other sessions where you can see demos of how this service works. And last but not the least, we have a whole bunch of videos, demos, hands-on labs, Jumpstarts, internal, detailed videos that go through the inner working. So, aren't you excited? Now that your databases can run in truly hybrid multi-cloud environments in Azure as well as outside Azure, using the same tooling and same experiences that you have used in the past, with a little more knowledge of Kubernetes, you can truly deliver database as a service for your application owner if you're a database administrator, and as a developer, you can write cloud native applications that use SQL, because SQL is evolving for helping you use the cloud wherever your cloud runs. Special thanks for supporting us, and so you as the community mean a lot to us. You've been making SQL such a successful product for our customers, for your customers. So please continue to use SQL, and we'll bring other data services to use in the future. Last, 3 ways to win prizes. We care about your feedback. Post a selfie if you like this. Give us session feedback, conference feedback. How can we make this better for you? I truly rely on your feedback to make my presentation better. And follow us on this. Again, thank you very much for the opportunity. Thank you for attending the Data Platform Virtual Summit, and wishing you more enjoyable sessions at the summit and a safe and healthy future. Thanks. DJ Data signing off.